All right, so let's start out by doing answering why there's like a jagged response in your simulations. So it's pretty straightforward. I want to make sure you follow so there's no magic. If you go and let's go ahead and put this in here just so we have it. And this is here. And then there's our nice little simulation, and we have 10 millivolts. And now, I don't remember the homework problem. Did it specifically say that you had to use, come on up, Henry. Did it specifically say you had to use a transient, or did I put that in there? All right. You guys are all like, yeah. Okay, so let's run this, and I'm going to show you how to fix this, because this is kind of a real subtle little point. I want to make sure you follow. So if I look now, and I'm going to plot the current through here, and then I'm going to take and how do I find the output? Well, let's plot the voltage too, just to show. And then the current, let's add to, let me just fix this. Let's go start at, actually, let's add plot plane, pull this up, and then I'm going to change this current here to go, how about I do this, 11.89 microamps. .089? Wow, you know. Oh, sorry. You did? Poor instruction. So you see how that's got the jagged shape, right? The reason that's there is because of numerical simulation issues. So in a SPICE simulation, it says to itself, when I get below a certain level, I'm going to say that the simulation's converged, and I'm going to move to the next point. So if you go up to and I'm going to show you how to fix that. If you go to the control panel and you look at the current tolerances, it says, hey, it's a current tolerance of 10 microamps, but also there's this relative tolerance here that everybody sees, which is 0.25%. So when, like for the first 20 years I taught, when we would do SPICE simulations, because I wouldn't pay for the money for real simulators because they cost hundreds of thousands of dollars, I'd use the free ones, and the free ones always had convergence problems. So I know a lot about SPICE problems, all right, because things wouldn't converge. And I say that, what does that mean? The simulations wouldn't run. They would say, hey, we can't converge because this node's not behaving or whatever, all right? So going back to this, you see that the voltage tolerance is 10 microvolts. I'm sorry, I read that backwards. And the current tolerance is 1 nanoamp, right? So if I go look, if I have a current flowing in the node, it says, hey, whenever that current gets to within 1 nanoamp of its value. Do you guys take a numerical analysis class anymore? Numerical analysis where you do like numerical iterations. There's a simulation technique called the Newton-Raphson iteration that you keep iterating, and when the residue gets below a certain value, you know you're converging on the simulation. So like if this is your value, you might start here, then go here, then go here, then go here, you know, and then you can keep going, but you never actually get right to the correct value. Okay, so you stop when you get within a certain range, okay? And that's called Newton-Raphson. Actually, I did my thesis on that in a numerical simulation. You can look that up at Wikipedia or whatever. So it says, hey, whenever this current gets within 1 nanoamp, so this variation becomes within 1 nanoamp, it says, I'm going to stop simulating. But what if you have a 10 amp current? Well, it's kind of ridiculous if you stop simulating when you get within 1 nanoamp, because that's like tiny compared to 10 amps, right? So there's this other term in here that says relative tolerance, 0.25% or 0.0025. And so if I go back over here and I ask what the current is, if the current is within the value that you're converging is within 0.0025, it'll stop. So for example, if this current was, if you simulate for a long time, was 10 microamps, then you did 1 microamp, which would move there, 0.1 microamp, which would move there, and then a quarter of that would be like, I don't know, I'm guessing like 2 nanoamps, whatever it is, all right? When you get within 2 nanoamps, you stop converging, right? So you move to the next point. What you're seeing here in the simulation is that it's saying, hey, I'm getting within, and this looks like half a pico, oh, sorry, I used nano, I should have, well, no, that's probably all right. I'm getting within half a picoamp of my actual current, and I'm stopping even though it's moving. And so this is numerical error, all right? So how do you get rid of that if you want really small currents? You choke down your tolerances. So I go over here and I say, okay, I'm going to go back. And I'm going to go to the control panel, and I'm going to change that to an order of magnitude smaller. And I'm going to change that. This still may be too big, but let's see what happens. And then I hit run. And I'm going to have to choke them down a little bit more. Anyway, you get the idea, right? So if you keep choking them down, yeah, it's not liking it. 15, let's put another 0 there. And LT Spice, these aren't like the older simulators where they would actually use these. A lot of times in LT Spice, they don't even look at these. And so I can keep doing this, and I found that out the hard way. I'm like, what the hell? And it'll just keep giving me the same waveform. So it's basically numerical error. So let's see what happens if I choke them down and more. Yeah, see, it's not doing it. So here, let's Google that real quick. Yeah, this is like a whole can of worms on there. So the answer is that you couldn't do anything because it's a numerical error that's showing up in the simulation. Okay, so it's not something to get worried about. Now, having said that, if you look, just for future reference, in the end of chapter 1, which covers SPICE, and if you look at oops. If you look here at the bottom of page 27, it says some common mistakes and helpful techniques. And so these are what you look at when you start having problems. And if you go to the next page and you look, what you see is, let me see if I can find it. Jagged plot is not specifying a print step. Oh wait, this is time display, that is X time axis. So this is another thing, a print step size. So let me try that one. See, I even forgot about that one. What's that? Adding R shunt, well, that'll help with convergence. Actually, I should have updated it for LT Spice, but with the dot options plot win size. But let's try the print step size and see if that's the issue. I don't think it is. I think it's the abstall and all that. But let me just try it real quick because I forgot about that one. So tell me what to do. Yeah, I'm going to right click on this and go to maximum time step. And let's change it to, how about something like a microsecond. Hit run, or actually let's, yeah, I don't think it's going to matter, but nope, I think that's numerical noise there. You can see that it changed a little bit by the simulation. But let's see. Yeah, simulators, that's why you got to know what's going on because they have limitations and you can hit them. Yeah. Well, but the VDS is different, right? So if you look, the drain current of M5, this one, it's giving a different current than this one? Okay, so that's ID of M7. They have to be the same. There's no other place for the current to flow. Oh, you're talking AC wise. Oh. Well, it's when you're down in picoamps, that's in the simulation noise. So, I mean, you got to question what the results are. Yeah. Everybody got that? That's not hand waving, right? You can't realistically simulate something to infinite precision. And if you simulate it to 1 picoamp, which is what we're seeing here, that's 1/1 billionth of an amp, whatever 10 to the minus 12 is. That's tiny. All right. So, I mean, if you go down, you have to do some special things with the simulator to get it to accurately simulate at that current. Okay. All right. Any other questions on the homework? All right, little hand wavy there. I wonder if I had that problem last time or if what I did. All right, so today, must be saving the tolerances. Today we're going to cover about I don't know. We're going to cover more current mirrors. And what did I say last time? I said last time we would start out with the wide swing current mirror. And for, is anybody having that problem with Chrome? I don't know what the deal is. Everybody, it's all of a sudden, so it's right click and I say open a new Cognito window. If I open it like 1 out of 5 times, it works. I don't know, it's like magic. And what's that? Yeah, opening it in incognito works. I don't know why. If there's something in there, and I Googled it and it said go to the settings and a bunch of other nonsense. So what I wanted to do is go over this Cascode, and then particularly, are we missing a slide here? Didn't I draw one last time where it went up like this and over? You know what? I think I gave this to one of my students to scan instead of me doing it. It's going to feed my phobia of.
Does anybody have any questions unrelated to politics?
Why don't I pause on that one? Let's see. Go here. Unrelated to politics. All right. Okay, so I think we lost a slide. So let's go over here. And maybe I'm having a brain fart. Oh, wait, did I hit record? No, I did. All right. Oh, I think I did it in here. All right, so I won't go back and say, what the hell, you lost my slide. All right, so let's pick up there. I want to review that with the long channel with the wide swing operation. Okay. So you're going to help me. So for wide swing, wait, first off, let's ask some simpler questions. And let me do it on this piece of paper right here. And that is the following. Why, in simple terms, do I use a Cascode?
In the VDS, so you have a reliable output.
Pin that, right? I want to pin it to a known voltage. So that's if somebody asks you, why does that happen? It's because I want to pin this to a known voltage so that I don't have a change in my output resistance, all right? So that's the answer. But in our basic Cascode, which was this one, right? What was the drawback, the first drawback of using the Cascode?
You need a higher VDS on the.
Yeah, this needed to be VDS sat plus VGS. all right, which was across here, because what was that voltage? 2 VGS, all right? So then we said we're going to talk about the wide swing configuration. I said I would start out this lecture. Maybe we're going to have a take-home quiz in this class too, so if I'm wasting class time. It wasn't?
No.
The simulations and starting late because I couldn't get the video converted. That's Sony's fault. All right. Okay, so for wide swing operation, what you have is the following. And so I needed, what the hell? I am sure that I did the derivation with the 4. Didn't I do that? That was on those slides? No, it was? Oh, all right. Okay. All right. Guess I won't be a good eyewitness. I won't remember. All right, so I go over here, and then this was, I wanted at VDS sat. And this I needed to be greater than 2 VDS sat. And over here, I'm going to connect this up. And I connect this down here because, again, what does the VGS? The VGS is set here by, that sets the current mirror, right? And then over here, I'm going to come in and I'm going to set this device to have what? We just saw it on the slide. 1/4, right? So 1/4 W over L. Righto? And then that would make this voltage, because what's this voltage? VGS plus VDS sat. Yay or nay, Anthony C? Okay, so I got a VGS there and a VDS sat there, and I size this to 1/4 to get that voltage. And then I use, what do I use this device for? That was something we went over. Well, I could just connect, the first way I did it was I just connected this one, gate drain connected, right? So here I said I'm going to make it so the currents match better. And I'm going to do that by making this VDS the same as this VDS. And if I do that, I can add this device to do that so that this VDS matches this, because that VDS is the most important thing for matching. Everybody got that? All right, any questions? Okay, so now let's go over, well, let me ask this. Do I need to do this? Do I need to derive the output resistance again? Is it going to be any different than the other way we did it? No. All I'm doing is changing the biasing, but that's still AC ground. That's still AC ground, right? Everybody got that? Okay, so now I'm going to pause, and I want to go through some of the circuits in the book. Okay, and then we're going to go through and we're going to talk about this topology. Actually, you know what I'm going to do? I'm going to wait on the regulated drain and current mirrors and all that. Or actually, maybe I'll do that today. We're going to talk about the biasing circuits, and I want to do that in steps rather than doing it all at once. So I'm going to do it in the book, and then we can look at it with the simulations. All right. So if I go over, I want to look at the long channel biasing circuits, and I want to go through that and make sure everybody follows. Okay, so you're going to tell me what's going on here. Okay, so first off, what is this circuit right here? This is figure 2043 in the book. What is this right here?
Differential amplifier.
You're killing me, man.
It's a
Beta multiplier. All right, everybody got that? What's this right here? Startup circuit. You know, here's why I'm going over this. If I was a student and somebody threw this circuit at me, I'd be like, holy crap, what the hell is that? All right, and I want to dissect it. So what is the point of the beta multiplier? Why do we even put this in our circuit? Current that's independent of VDD. All right, everybody got that. So VDD changes, the current stays fixed. Lucas, you good? All right, and what's this circuit for? What is this circuit again? Startup, what's it for?
One of the states is possible, there's no.
Make sure this goes to the state I want, not zero current, because if it goes to zero current, I have nothing. Now, real simple. What is, now notice first, I've only got one output of my beta multiplier coming out, right? I'm only using that because I don't want to use this one and this one, because then I don't get all the benefits that I have of having one current, one power supply. Here, this current's going to change, the bias current here is going to change slightly depending on the bias current here, because here, let me pause and make sure this is clear. Does everybody understand the current in here isn't going to be precisely the current in here? Why is that in simple terms? This VDS isn't going to be the same as this VDS, and when we went over this, we showed the two currents are going to be slightly different, right? But I want all of the currents in these other circuits to track and based on only one current. All right? So what are these two transistors right here? They're NMOS, but I mean, what do they do? They're transistors too.
Or they have a different wavelength, so they multiply.
Oh, here's your gate drain connected one in the beta multiplier. They're current mirrors. They provide the bias, and then in this case, they provide the bias for a long L device and a wide swing cascode that's configured as a gate drain connected transistor. Okay, so let me pause. In what we just went over at the end of last lecture and this lecture, what's this? What is this transistor here and what we just went over?
That's the VDS.
No, I mean talking, yeah, that's right, but I mean simple terms. It's the transistor that's the 1/4 transistor, right? Okay, now, but if I look at this, the PMOS are 30 by 2. Here, I've got 30 by 10. It's not 1/4, it's 1/5. Explain to me, why did I make this 1/5 instead of 1/4? No? When I make it 1/4, remember we talked about this a little last time? Let me show you in a figure. Oh, PowerPoint's good. See in the figure here? When I, excuse me, when I bias, I'm biasing right on the edge of saturation and triode. That's with the 1/4. Okay, so let me make sure we follow that. So when I bias that, I'm biasing this transistor here right on the edge of triode because I made this 2 VDS SAT plus V threshold in. Just as a pause, what is VDS SAT plus V threshold in? VGS. So there's the VGS, so I pin this at VDS. So if I do that, I'm pinning it right on the edge. Everybody got that? By making this voltage higher, I still got the same VGS here. What do I do with this voltage? If I move this voltage up, what happens to this voltage right here? Goes up. If it goes up, what happens to the output resistance of M2? Goes up. Prove it. Go back to chapter 9. And if you look at how the output resistance changes with VDS. Huh, that's a typo. See that? The arrows, when I put this in, I didn't bring the arrow to the front, it's behind. Everybody see that? So this should have an arrow going up and pointing to this point right here that says this device starts to enter VDS SAT. And the arrow goes up, and then as soon as it gets to the graphic, the graphic's on top of the arrow. Anybody follow that? The arrow's cut off. You know, I can't read anything anymore without going crazy. Like when I read documents, if I see like 3 spaces after a sentence, it just jumps out at me from doing so much editing. So anyway, oh well, it is what it is. Let me just pause for a moment and see if that's on my list of typos, and I just don't remember. Come on. No one wants to see me giving blood. Come on. What the hell? All right, so, all right, I guess I'll add that tonight. Okay, so anyway, the device starts going here, but what do you notice about VDS? No, if I increase VDS, what happens to the output resistance? Goes up, right? So if I move the device up here, it got an increase in the output resistance. So I'm changing this device size so it's a little bit longer to increase this voltage and move this voltage up so that the output resistance goes up and I have higher output resistance. And just as a sanity check, and I don't mean to insult anybody, why do I want higher output resistance? So it behaves more like a current source, right? It's flat. High output resistance means it's flat. Everybody got that? Okay, so I go back over and I look at where we were just at, and I say, this is the device where my VDSG is going to be a VSG plus a VDS SAT, so that the voltage here is VDD minus VSG minus VSD SAT. Does everybody follow? Okay? And now you look here, this is just my normal wide swing current mirror. So I'm going to ask you a depth question I've covered several times now. I want you to tell me, what's the point of this device right here? This one right here. Simple terms. No, there's the current mirror right there. Okay, one more time. This device will act to make this source to drain voltage the same as this one so the currents track. What controls the currents in each branch? What's the biggest thing controlling the currents? The VSG, the VSG. What's the biggest thing controlling the currents here and here? VGS, VGS. What's the biggest thing controlling the currents here? VSG, VSG. So now you notice I take and I call this gate voltage V bias 1. I call this voltage V bias 2. And then I, just because we'll find this useful down the road, I'm going to call V high, which is VDD minus VSD SAT, a voltage that I can also use for biasing. Now, we'll look at this again next time, but you see this VN cascode? That voltage is going to be a VGS plus a VGS. So this voltage, there may be some situations where I want to have 2 VGSs for biasing. So here, I go ahead and throw that in, and I generate 2 VGS for the biasing. This V bias 3 comes from down there, we'll look at in a moment. Okay, so now, what have I done with this part of the circuit? I generated V bias 1, V high, V bias 2. I can use those now right here for the current sources that I use for my NMOS circuits. We're going to go over this again next time as well for the short channel process. Okay, So I look and I say, here's V bias 1. So everybody see this could be here, right? I mean, everybody sees this V bias 1. I'm just being lazy. I'm not drawing a wire from there over to there. Well, I'm not being lazy. That's the way it's done in industry or when you do projects. If something's named the same, they're connected even though you don't show a wire between them. All right? So I got V bias 1, V bias 2, V bias 1. So simple question. What do I think of these as? No, well, these transistors here, what do I think of each set as? Simple question. Current sources. This is a current source to supply current here. So when I'm lazy and I draw a current source, I just put a little circle with an arrow. But this is how I make that current source, just like here. I put a little circle with an arrow going down. I put a little circle with an arrow going down. I'm being lazy. That's the whole point. And then here I get my VDD minus 2 VSG. Here I generate my V bias 3 and my V bias 4 for my low voltage cascode or my wide swing cascode. And there's my V low. So I got a question for you. I just told you I think of this as a current source. Think of this as a current sink or current source, depending, they use that interchangeably. Which is better, this current sink or this one?
The other one, second one.
This one. Why?
This is more devices.
In simpler terms, why is this a better current source? If I replace this with a circle and an arrow, and I replace this with a circle and arrow, why is this one better than this one? Oh.
Like this circuit right here at the bottom is kind of a continuation of the one on top.
I don't ask complicated crap, man. I ask simple stuff.
To go through the cascode.
Cascode has higher output resistance. It means it's got a flatter response. It means the current doesn't vary. This one, the current is more steady. Yes, like this one, the current's going to have a little slope to it. It's not perfect. Does that make sense? So why is this better? It's cascode. It's higher output impedance. The current's going to stay more steady through here. Now, if you were to look at them, you might see that this one and this one have exactly the same variation in current with VDD, simply because this one is generated from this one. So now, tell me how to get around that. I could cascode here, right? Or cascode here. Okay? So I'm going to show you another way of doing this. That's for the short channel process using the beta multiplier. Then we're going to come back to the wide swing cascodes. But I mean, this circuit, there's a lot to it. But we're going to use this circuit for examples throughout the rest of the semester. And I'm going to expect that you know what V bias 1, V bias 2, V bias 3, etc. are. Okay, any questions looking at this? Now, if I use this circuit for the short channel process, I go back over and I look, here, let's actually show you. Man, I'm loving this PowerPoint. I go back over, and where's the beta multiplier? I want to do a couple things first. And I look, and I plot the current in the beta multiplier for the short channel process. It looks like crap. Everybody see that? VDD is varying, the current's varying a lot. But what the design we use is the following, and this is how we get it to work well. It has this, and we've added this circuitry right here. Okay? So I'm going to pause, and I'm going to go over a couple things. We've covered how the currents change with VDD, but we haven't covered how they change with temperature. And I'm going to cover how adding this amplifier stabilizes the current. And then we're going to look at that for a wide swing current mirror with the V low and all that stuff. Okay, so let's do the let's do the following. All right. I'm going to ask you some simple questions. I want you to burn them into your brain, all right? Of course, I want you to do that with everything I teach. All right, so first question. Does anybody remember how the threshold voltage changes with temperature? As temperature goes up, what happens to the threshold voltage? Goes down, it gets smaller, it's increased temperature. What happens to mobility? Goes down. Remember, mobility goes down, threshold voltage goes down. So let's say somehow magically I was able to get a constant current flowing through this current here. I'm telling you this I is constant. And I want you to tell me, how does I vary over here with temperature? So I start changing temperature. If I go up, doesn't the threshold voltage of this change? Goes down. But how does, and I'm telling you this current doesn't change with temperature. How does the current over here change? Okay, so this is the thing I want you to know. When I look at this and I say the current flowing here is constant and doesn't change with temperature, this one doesn't either. Why? The source to gate voltages can be changing all over the damn place, right? But that doesn't, the threshold voltage could be varying, the mobility could be varying, but that's not what matters. They're all changing together. This threshold voltage change together. This mobility and this mobility change together. Prove it. I will. M1, M2, 2. So let's do I1 over I2. And if you remember, that's mu sub n Cox prime over 2 W over L times VGS minus V threshold, or threshold P, VSG and P squared. And that's all over mu P times Cox prime over 2 times W over L times VSG minus V threshold P squared. And if I ask you now, how are the VSGs related here? They're the same. Why? Tell me. I'm going to ask you questions interviewers will ask you. Why? Why are they the same? They're tied together. The two wires are the same. They got to be the same. They'll ask you that. Are you sure? Are you sure they're the same? Let me see. These are the same wire. Yeah, I'm sure. Okay? When you get deposed in lawsuits, especially when you're first doing it, they like to do that to try to have you question yourself and sound less sure. You sure about that? You sure 1 + 1 is 2? You sure? And then there'll be a long pause. They don't try that crap with me anymore, but they used to. Well, I've been deposed 58 times, so I mean. What's that? I love silence. If you are questioning people, like if you get arrested or whatever, first thing, always call for an attorney. I always tell you. Next thing, when they're interrogating you, they like to say, you stole that, didn't you? And then when you say, no, I didn't, and you try to deny it, they'll wait for a long pause, because it's human nature. You become uncomfortable when you're having a conversation and there's a long pause. You love pauses. No, I'm innocent, but I don't know the law, and I think it would be better if I had somebody that did. I need an attorney. No, I'm not guilty. I just want my attorney. I don't want to say anything, you know. Seriously, you got to take this crap, because they can get you to say stuff that can hurt you, all right? And they don't have to tell the truth. They can lie, okay? All right. Always looking out for your well-being. Anyway, so what happens to mobility there? I just don't like people getting treated bad, and yeah. What happens to the mobility as it changes with temperature? Who cares? Divides out. Right? What happens to the VGS minus V threshold? Who cares? Divides out. Cox divides out, and all that's left is the ratio. All right, good? All right, so you're telling me that with temperature, these don't change. Now, if it comes down here, and I'm going to go like this, and you're going to remember the reason I gate drain this and gate drain this is so as VDD changes, these two voltages can move in opposite directions, because I want there to be a voltage change across this NMOS. And this one, I want to be able to have the voltage change, so I can change the voltage but the currents stay essentially the same. So now, if you recall, I want to look at, and I'll actually just, do you remember what the current was in this circuit? I from memory? I'll try to do it if you don't.
One over M R squared. Over squared.
Oh, wait, yeah, this one doesn't have that, right? And then this would be K times wider. So if I ask you, a 2? All right, I don't remember. I was just hoping you would tell me. Okay, so if I ask you, okay, how does temperature affect the currents in the beta multiplier and why? It doesn't. I mean, how does it affect the threshold voltage change with temperature affect the current? It doesn't. I can see it from the equation, but more importantly, I can say that threshold voltage changes in each part are subtracting out because it's a difference in the two. Who doesn't understand that? So you would agree this node is common to both, right? You would agree, that's another thing attorneys like to do. You would agree this, you would agree this, you would agree this, and they get you saying yes, 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 till the important one, and then you say no. You would agree you were on that street corner, wouldn't you? Yes. You would agree when they were there when I was getting robbed? Yes. You were the one that robbed, didn't it? No. I'm paranoid at this point. It doesn't matter, man. They have to know the right words. All right, so they have to know the law. All right, so this voltage is what? And if I put in for the equation for the threshold voltage, what happens? Divide out. So then your answer is, oh, threshold voltage doesn't come into play. So what comes into play here? Mobility and resistance. So if I look at this, I've got 2 over mu times C aux times W over L. Does W and L change with temperature? No. This is R squared. If you go through, and it's in the book, as temperature goes up, what happens to mobility? Goes down. Let's make sure you remember this, because the threshold voltage going down, you can remember this, that if you put your phone in the windshield of your car in the summer, sun hits it, the threshold voltage, those billions and billions of transistors on there, it's going to drop. They drop too much, transistors are going to stop behaving like switches, they're going to be leaking like crazy. Your phone will stop working. Okay? So that's the way you remember the threshold voltage goes down as temperature goes up, because if it's going down, the threshold voltage is going to start causing the transistors to leak. If it goes to 0, then you're going to get a current flowing with no voltage applied. Okay, so your phone stops working. Mobility is like if I'm driving my car on the freeway and I need to get to UNLV because Dr. Baker wants me to be on time. He's like a stickler about being on time. And you're like, there's a zillion cars on the freeway and it's getting hot and there's more and more cars. Well, that slows down your mobility, right? Or if the weather cools down and everybody's enjoying the weather and they're on the freeway and like, this is great, you're more mobile and you can get through faster, right? No interactions, people are listening to the music and enjoying the drive. They're not hot, their AC's not broken, etc., right? So mobility goes down as temperature goes up. What happens to resistance as temperature goes up? Resistance goes up. Something becomes more resistive as temperature. It means it's harder because I've got all these vibrations in there that's harder for me to push something through because there's more collisions, all right? So as temperature goes up, mobility goes down. I'm having a harder time getting to school. And my resistance, it's the same thing. The resistance goes up. I'm having more resistance on the freeway. The damn people are driving slow. Get going, I got places to be. Right? Drive slow and let people in, especially in Las Vegas. It's a tourist area and you want to get people relaxed. Unless you're driving from way the hell out there and you're spending your life in your car, then I gotta get to where I need to go. When I drive, I purposely try to be nice, let people in and all that, because I don't have to drive very far and I want it to be relaxing. I didn't think like that when I was younger. Now I do. Days are ticking away. Any questions on this? So what's the takeaway from all of this? Temperature is good for the beta multiplier because the mobility decreasing is canceled by the resistance going up, and the temperature or the current stays essentially constant, right? Doesn't move a lot. It's still going to move, just not going to move a lot. You want it going and changing. Okay, so any questions on that? So now let's look at something. Suggest a way to make this circuit so that it's less dependent on VDD. What's that? Cascode. Let's cascode it. All right. So let's look at, in the book I showed you that it would if we, I'll just show you real quick since we got it up. If we were to, if we were to just look at the beta multiplier for the short channel process, you would see this huge resistance. So I want to try or this huge variation in the current. So I'm going to try to cascode. But I'm only going to cascode one size to try to make the variation smaller so that they don't vary as much. All right? And you know what? Instead of drawing this, I'm going to take this simulation and we're going to modify this just to show you what happens, okay? So that's 2018. All right. Yeah, my car, I drive in my car and I used to think it's old, it's 20 years old, and I used to think that, you know what I'm going to do? Oh, crap, I don't have the LT Spice models here. You know what I'm going to do? My CD player stopped working. The cassette player barely works. So for like about 5 years ago, for the previous 10 years, I would always think to myself, I'm going to buy one of those cassette inserts with a jack you can plug in so that you can listen to your phone on your car. All right. Well, I've waited too long because I have a phone that doesn't have a 3.5 millimeter jack, and my cassette player no longer works. So my CD player doesn't work and my cassette player doesn't work. So I can't listen to music other than the radio, which is fine. All right, extract here. What's that? I can't do, how do I do Bluetooth? My car doesn't have any of that. I have a car with a cassette player and a CD player that doesn't work. Every time I get in, I hear click, 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 click. And I keep thinking to myself, I'm going to fix that, rip it apart. And I'm like, yeah, I don't care. What's that, Cody? Yeah, my radio works. A Bluetooth. Yeah, see, I should do that. I should get like an auxiliary. Now I'm going to think about that for the next 10 years. Then my radio won't work. I'm not into cars. I mean, my wife has a brand new Tesla, and I'm going, whatever. All right. I just want a car that works. And I was driving this morning, and I was thinking, hey, I wonder how much longer till this car has a problem and I'm stranded or whatever. And I'll deal with it when it comes. If it works and starts, that's all I care about. All right. So this is the circuit. Let's look at the sim real quick. And you see there's the resistance. So now, this is going to be really instructive, I think, if you understand what's going on. Actually, I'm going to, just to simplify things and see if I can get away with removing the startup circuit. Hit run. All right, still working. So just to simplify my life, I'm going to get rid of this. And then I'm going to go here, grab the hand. The problem is people say that you need, these old cars, like my car gets like 13 miles to the gallon. And they'll say things like, you're bad for the environment. No, getting a new car, the energy that goes into making a new car is way worse for the environment than that. Anyway. All right, so let's go here. Let's get the scissors out. And I want you to tell me, first off, what do you expect is going to happen here if I cascode this side? So I have to try to keep these two currents the same, right? But when I change the VDD, don't I still change this voltage? And doesn't this voltage remain essentially constant? So it's going to be better, but it's not going to be perfect, right? Now, I want you also, before we go any further, to estimate the minimum VDD, because before, our minimum VDD was like, I don't know, guess like 0.4 volts or so, 0.5. What's going to happen here? I need to have a VGS here, which is 0.35, a VGS here, which is 0.35 or 0.7. And then if I go here, this is 0.7, I need to have a VDS sat, say 0.05. So I'm going to be almost at a volt before, like 800 millivolts before this turns on. So I hit run, and I see that, hey, it's matching better, but it's still not perfect. The output resistance is still bad. Everybody see that? So then I ask, okay, well, so everybody sees the currents are matching better. Everybody got that? They still have a large dependence on the VDD. And more importantly, I can't go to as low a voltages. I'm only going now to like 0.85 volts, whereas before I was going to like 0.45. Does everybody see the problem? Okay, so here's what I'm going to do. Oops. I'm going to try to, let me draw it. I don't like pointing to stuff. I'm going to try to equalize the circuit so that this node and this node are the same. I'm going to add an amplifier in here that looks at these two, and I'm going to adjust the gate voltage here to provide, and I can make this gate drain connected, but I'm going to try to set these two voltages to the same value with this amplifier and adjust this so that the two currents are the same. So if I do that, then I can actually allow these two to stay the same voltage, but on the other hand, both of them can go up with VDD. So let me show you this. Let me sketch the circuit topology. So first off, before I go any further, does everybody see that when I do this, if this is gate drain connected, this is going to be one of the situations where I know the input of my amplifier has a VGS there and a VGS there. Everybody got it? Okay, so I'm going to put an amplifier in here that I can use that will work when I've got a gate source voltage. And so what I'm going to do is I'm going to do the following. This is going to be my amplifier. Let's go this way. So what did I just draw? Current mirror. Then I'm going to come down, and then I'm going to come down here, and I'm going to take this point and make them this point and this point. Then I'm going to take this as my output and connect it here. So I'm going to do this first. Instead of using a transistors, I'm going to just simulate it with the voltage control voltage source. So let me go over to, it's probably like this figure right here. And what I'm going to do is I'm going to take, and I'm going to look at this point, and then I'm going to, instead of gate drain connecting this, I'm going to connect the output of the amplifier to the voltage control voltage source. Everybody see that? Okay, so now, first question. I need to have negative feedback or else it's going to, I'm going to have like a screeching amplifier, right? So if I ask if I'm feeding back, because these two are the same transistors, and so if I move this up or down, I'm going to get a signal that goes through here and a signal that goes through here. Okay? Which one is going to have a larger impedance? This side, the signal going through, or this side? Yeah, this side, the one with the transistor and the resistor going to the drain. Okay, next question. If that's the case and I need negative feedback, why did I tie this node to the plus terminal here instead of to the minus for negative feedback?
When the gate goes up, the SP goes down.
Yeah, when the gate goes up, this is acting like an inverting amplifier. It inverts the signal that I feed back, because if the gate goes up, it shuts this off and this goes down. So this inverts the signal that I put at the gate. One more time. Does everybody agree that if this node goes up, it shuts off the VSG of the transistor? Does everybody agree that if that happens, it shuts this transistor off? If it shuts this off, doesn't it allow this node to go down? So doesn't that mean if this is going up and this is going down faster than this one's going down, that I'm going to get negative feedback through here? This going down in the negative direction will be added faster than this one going down and have a net negative effect. So I know that's confusing, so let me try numbers. This goes down by 2 volts and this goes down by 1. When I do 2 minus 1, so this is minus 2 minus minus 1, I get a net change of minus 1 volt times 10 means a net change here of minus 10. Because this is going down faster than this one. Kayla, you look perplexed, so let me try it again. Right, so one more time. So I determined this is a higher impedance than this. I note that when I move this up or down, I'm turning on and off these 2 transistors. These 2 transistors provide a current through each side that's the same. So I want negative feedback. I want, as I adjust this signal here, for one of these to move at, the one that's got the negative feedback to move more than the one with the positive feedback. Because then when I take it's just like this. If I get on the loudspeaker, or I get on the microphone here, and I say hello, and it comes back through the speakers, and it hits this louder than my hello voice, then it gets amplified again and comes back even louder than that, and you get that screeching noise, right? However, if when I talk, it comes back and it's quieter, then it gets amplified, but since it's at 0.9 of my voice, it amplifies a little lower. Then it comes back at 0.8, gets amplified a little lower, then it's 0.7, gets amplified, and it dies out and it stays stable. I don't get the screeching. Is anybody taking, what's feedback and control here? 370. Is anybody taking that? Is that good, Cody? All right. So, you know, what's the best way? You know, that's one thing. When I took feedback and control, and I'm like, what the hell? It's just a bunch of blocks. And then I got out and I started working. I figured out that you probably have seen me do this, where I do this. Like, this is a great example of a feedback control system, where this is your in, the in. This is where you take the difference, your difference. This is the beta network, so this is your V out. So the beta is fed back, and this would be beta V out, which is just the voltage divider equation. And I started, the hell? Why did they teach me that? So I knew all this crap was useful, you know, or give examples like that. Anyway, all right, so let's go look at the examples, and let me look at the quiz. I feel bad giving you such an easy quiz as a take-home. No, it's not. I don't want you to feel ripped off. Holy crap, these are easy, man. All right, we'll give it to you to take home. But what I want you to do is I want you to work it on one page. Then I want you to do the SPICE and attach it as a second page, only a second page that verifies your hand calculations, and turn it in next time. I want everybody to get 100%. And of course, it's not the same as a homework assignment. Why? Because it goes towards your quiz grade. So if your quiz grade's poor and you get this free quiz, you have a free chance to boost your quiz grade a little bit. All right, everybody got that? So why don't I start passing these around while I go over the last little bit, then we'll quit on time. God, I'm becoming a softie, man. What's wrong with me? All right. So let's go replace that. And let's look at the circuit. And so here you see the amplifier, but I did something a little different to make it even more stable. I gate drain connected this side, which had before. I broke the loop between the two because I'm holding them the same. And then I gate drain connected this side. So the amplifier, if this is VGS1, will try to keep this side of VGS1 as well. So what's this voltage? It's VGS1 minus VGS2 over R1. All right, and so here, you remember what it looked like before? I don't think you do. This is what it looked like before. If I didn't mess it up, I hit run. Comes up, looks like crap. Here's what I have for my modified circuit. I come back, I hit run. And I look, and look how nice those currents look. And look, it's also turning on at about 0.45 volts and not 0.95 like I had before with the Cascode structure. That quiz isn't hard, man. I feel ashamed giving it to you. It's so easy. Right, Hisham? I don't know. I haven't seen it yet. It's still making its way around. All right, so here's an important thing. You see how I have a feedback, but as I went over a moment ago, what's the problem with feedback? Why we study, and the whole point when we do feedback analysis? Stability. I got to stabilize the loop. I got to make sure that things don't move too fast. So I want to show you, and this has actually happened. I told you this, I've had problems with stability in this circuit. So what I'm going to do, I put this capacitor here on the on the output of the amplifier. So here's the output of the amplifier. I put this capacitor here, and now I'm going to remove that and see what happens. So I'm going to axe that. This one's not in, this is on an input, so I don't think this one matters. I'm going to hit run. So now I don't have that capacitor slowing things down. Oh, maybe it does matter. Oh, wait a sec. Can I see stability in a DC sweep? Nope. So let's go do this again where I do a transient. Let's go over here, and I'm going to just do a dot tran. And let's do 100 microseconds. Let's see what happens. And I hit run. And I look at the two currents. And actually, you know what let's do? Let's be fancy. And let's pulse this from 0 to... Did I tell you I went through all of the LT Spice? Okay. Because what a pain in the ass. Anyway. Yeah. Yeah. So anyway, let me do this. So I'm going to put a 50 microsecond rise. And then now I have to put all this. It really is a pain, but whatever. All right. So I'm going to pulse the VDD up to, we can look at VDD while we're doing this. Pulse it from, what? I thought I put 50 microseconds. Oh. I only got 3 minutes to get my point across. 2 minutes. You see I'm raising the VDD. You see how the source turns up, right? Life is good. Now let me get rid of these capacitors here. Hit run. What? And hit run. Yeah, this one shouldn't matter. And you're killing me. Let me pulse this. When I want instability, I don't get it. Let's just say none, DC value 5, hit OK, run. Here, you know what? Because we got stop. Let's go over to here and hit run. Oh, crap. Guess I missed one, huh? See that? I just downloaded this and I missed this pulse. So I got to go here and put, T fall 10p, which I won't even like 1 millisecond. It's not going to do anything. And hit run. And you see how now it's oscillating? I don't want that. So I'm going to go get the scissors here. And then I'm going to come down and I'm going to go boom and hit run. And now the currents go up. And let's show them here. It's showing the when startup transient, but you can see once it gets going that it's nice and stable, right? So I need to make sure the loop's not too slow or too fast. I need to slow it down. All right, have a good weekend. We will see you on Monday, and I will talk about regulated cascodes and all that crap, and you'll turn in your quiz. And we will probably have another quiz. And is there a homework due on Monday? Yes or no? Let's see. How damn nice I am.